We have a mass sample of magnesium hydroxide, a mass sample of hydrochloric acid, which is already kind of nice because typically hydrochloric acid is dissolved in water, so a mass sample actually is nice because we're telling you how much hydrochloric acid as opposed to a volume. Okay, so we've got a nice little shortcut here. At the end of the reaction, a chemist recorded a dry mass of 60.0 grams of magnesium chloride. What is the percent yield? Okay. Well, how would you calculate a percent yield? I know we just talked about it, so it's a bit of a stretch, but how do we calculate percent yield? Actual over our theoretical or calculated. I always wrote theoretical, but calculated I'm starting to grow a little bit more attached to so that we acknowledge that we have to calculate that term. Okay. And then times 100%. Are we given either of those values in the question? Well, actual yield of what? Calculated yield of what? I'm given masses for 3 different substances. So until I know where my product is, because it's what I'm going to be looking for, or what my product is, this is going to become kind of a difficult question to answer. Okay, so one of our first steps should be write out the chemical equation. Okay, what happened? So I took magnesium hydroxide and I reacted it with hydrochloric acid. Okay? Both of those now in that statement are now reactants. That probably means that last number provided there, the magnesium chloride, is now my product. Okay? But let's verify that through the chemical equation. So in our first step of this, we would have to convert those names into formulas. Well, magnesium has the formula Mg, hydroxide has the formula OH. Magnesium's a +2, hydroxide's a -1. That formula is not correct. I would need 2 hydroxides to balance. Right. Plus, notice I'm not given the phases, so in this case I'm just going to kind of ignore it. Okay, because it's not critical for this. Hydrochloric acid. Okay, so again I have to break that term down. Technically that one does include the phase. Hydro is only used for binary acids, so I'm looking at hydrogen because it's an acid bonded to chlorine. The charge on hydrogen is a +1, the charge on chloride -1. Those charges are balanced, that's the correct formula. This would then undergo a chemical reaction. What kind of chemical reaction do you think we'd go through? This is going to be a double replacement. It's a little bit tricky because what we're replacing are the 2 positive charges with each other, the cations, but they aren't both metals. Okay? But hydrogen can act like a metal. So what we're going to end up doing is exchanging those 2 species. So I'm going to bond hydrogen to hydroxide, and I'm going to bond magnesium to chloride. What is the charge on hydrogen? What is the charge on hydroxide? Is that formula correct for HOH? Yep. Okay. What is the charge on magnesium? A +2. The charge on chloride? -1. That formula is not correct. I would need 2 chlorides. I've now done the double replacement, predicted my products, made sure my products are correctly drawn out. This can help us out because when we go through and look at this, we're producing 2 products, water and magnesium chloride. Within the question, we're told that we obtain 60 grams of magnesium chloride, which means that 60 grams is an actual yield. So I could go through and plug that number, 60 grams magnesium chloride, into the calculation. I don't have to calculate it, it's given. Right? I would then need to divide that by the calculated yield. Right? Well, that means I have to do a calculation. That's why we call it calculated. Right? So how do I go through and determine that? Okay, well, that calculated yield or our theoretical yield is based on the limiting reagent. I'd go back through and say, well, in this reaction, how much could I possibly have made? If everything went absolutely perfectly, how much magnesium chloride could I make? Okay. This isn't just to look at it and now I know the answer. This is actually running a calculation. So what I would start off with, assume a perfect reaction with the magnesium hydroxide. So I started with 50.6 grams of magnesium hydroxide. I want to know how much magnesium chloride I could produce. And in particular, I would ideally like grams of magnesium chloride. Why grams? Well, for my theoretical yield, I want the units to cancel out when I calculate percent yield, so I want the grams of magnesium chloride so the units cancel. Are the grams of magnesium hydroxide equal to the grams of chloride? Are they the same thing? No. The measurement's the same, the substance is different. So I'm going to have to do a substance conversion. What unit do I have to be in to do a substance conversion? Grams does not allow a substance conversion. If I give you 500 grams of bicycle tires, how many bikes can you make? How much does a bicycle tire weigh? Okay, you need the count. The only way we can convert between substances is through a count unit. Okay, the number of those species there. Because we're in chemistry, the count must be a really insanely high number, so high that we don't want to deal with it. We use, that would get us up to it, we would use moles. Okay, so moles is our count unit. If I'm in the measurement unit of moles, I can now convert the substance. Am I in the measurement unit of moles? No, so what do I have to do? If I need to be in moles, how about I go into moles? Okay. Is that a conversion factor that I'm responsible for either knowing or knowing where to find? Yes. Where is that found? That's on our periodic table. So magnesium is, because I don't want to carry all those numbers, 24. How many oxygens are there? 2, because that parentheses applies forward. Oxygen is 16 times 2, 32, plus 24, 56. Hydrogen weighs 1. There's 2 of them, so 56 plus 2. That one I could do pretty well. Gotcha. Thanks. Appreciate it. So 58 grams is 1 mole. I'm now in my mole unit. What was special about the mole unit? Now I can convert substances. So the moles of magnesium hydroxide can now be converted into the moles of magnesium chloride. Where do I find that conversion factor? From a balanced chemical equation. I have a chemical equation. Did I balance it? No. So I got the idea of my product that helped out, but now I actually have to use the equation. To use the equation, I have to have a balanced chemical equation. So I'd go back up to my equation and attempt to balance it. Hopefully what you will find is that we need a 2 here and a 2 here. What is the relationship between the moles of magnesium chloride and the moles of magnesium hydroxide? 1 to 1. I now have units of moles of magnesium chloride. What unit do I want for an answer? Grams. So the moles of magnesium chloride needs to show up in the denominator so that the unit can cancel. Grams of magnesium chloride needs to show up in the numerator. Where do I find that conversion factor? From the periodic table. So 58, right? Because I got the 58 from the periodic table. So I should put 58 grams over here. No, why not? The 58 is for magnesium hydroxide. I want for magnesium chloride now. So I have to go back to the periodic table and recalculate. The chlorine comes in at 35 times 2, 70, plus the magnesium at 24, 94. I get 94 grams is 1 mole. I could then go through and punch stuff into the calculator and get a magical answer at the end of that, which looks like it'll come out close to 100. 82. Thank you for the calculator. Okay. Ultimately, 82 is wrong. 82.0. Don't those mean the same thing? Yes, but 82.0 has 3 sig figs. Okay, and we need to carry 3 sig figs. So that could be my calculated yield, because I've now calculated it out. Okay. However, that assumed I had more than enough hydrochloric acid. Was I told the amount of hydrochloric acid I was given? Do I know that's more than enough? Unfortunately, no. So what do I have to do? The calculation all over again. Just like we did with every other limiting reagent calculation. We'd start with, whoops, we don't start there. Start with the amount of magnesium chloride. That says chloride. At the end, I'm starting with 45.0 grams of hydrochloric acid. Okay. I'm converting substances. The only unit I can convert substances through, moles. So what do I have to do? Convert into moles. Where do I find that conversion? Periodic table. Chlorine was 35, hydrogen is 1, it needs to be 36. Okay, I'm now in moles of hydrochloric acid. I don't want that. What do I want instead? The moles of the magnesium chloride. What is the relationship between those?
2 moles of HCl.
2 moles of HCl equals 1 mole of magnesium chloride. It's literally the coefficients from the balanced equation. I then need my molar mass. The moles of magnesium chloride. Whoops. And I'm converting that to the grams of magnesium chloride. That information is found on the periodic table, or I already calculated it. I can put up the 94. I can then punch this through into the calculator and I get 58.8 or 59. I would argue that those are a rounding thing, and it may very well come down to somebody said that my rounding of 36 was a bad idea, which ultimately it was, because chlorine is 35.45. Okay? So now we have those 2 numbers, so what do? Which of those 2 numbers should I plug in for my calculated yield? The smaller of those 2 numbers, because that is the most that I could make, which seems kind of weird, but that's how it works. Once I achieve 58.8 grams, I'm now out of hydrochloric acid. Right? I don't have enough to make more. So I'm done at 58.8 grams. That is now my calculated yield. I can now dump that back up into my equation, 58.8 grams of magnesium chloride. Go through, multiply by 100%, and I get those of you who are punching in the calculator can tell me a number.
102.
Okay. We're going to stick it at just 102 because we have 3 sig figs, so we get 102%. What do most students do when they see 102%? You can't have 102%, so what does that mean? I used the wrong number, so it should have been the 82. No. No, it shouldn't. Okay. Just because you have over 100% doesn't mean your calculation was invalid. It does give you pause to go, oh crap, something's wrong. Go back and check your work. Okay. Check the work, you will find it is spotless. Okay. Because you helped me do it. So good job. So how did we get 102%? That's a much harder question. Can't make extra, because I literally run out at 58.8. I can't make any more than that.
Well, I was also told you couldn't make 102%.
Okay. These were likely all done in what phase? In aqueous phase, because those are easier to work with. Gases tend to be toxic, not healthy to breathe in, so we put them in an aqueous phase. So presumably our magnesium chloride would have been a solid, so we could have extracted that away from the water. How would we have separated the solid from the water? Filter. So when you filter, the solid that remains has absolutely no water in it. Okay. We could go through and reference coffee for anybody that's drunk coffee or worked at a coffee shop. You know, you just put the water through the coffee grounds. The grounds come out and they're spotless dry. You can just throw them away, right? Okay, now there's this nasty wet mess. Why are they still wet? Wasn't the whole point of the filter paper to separate the solid from the liquid? There's still extra liquid in it. Right? How would we in lab limit the presence of that liquid? You would heat it up. You would evaporate off the solvent, like we've done in lab on multiple occasions. Right? Because our lab time gives us enough time to be able to do that, our product is almost always dry, which means we're under 100%. But what if you didn't have a lot of time? You probably have a little water left, which means your mass goes up. So the 102% doesn't mean I have 60.0 grams of magnesium chloride. That's just happened to be what I measured. That 60.0 grams of magnesium chloride likely has water in it as an impurity. So why even throw a question like this? Because this isn't a lab class right now. It's a lecture. Why are we putting this up here?
We're going to do it in lab.
Right? Because we're trying to set you up with the real world. We'll see it in lab. You need to be able to think about those extra steps because it can happen in the real world. So what we do is set you up with a real world example, and then you go, well, it's not the real world because I'm in class, so I must have done something wrong. I'm just going to change to a different calculation. You did everything right. You have to know what you're doing, otherwise you will get the answer wrong. Because believe it or not only will 102% be an answer, so will 60 divided by 82. That will be a provided answer. Okay? So it is not a question of just punching numbers in until you get an answer on the multiple choice. Every answer on the multiple choice is possible by punching numbers in.
So to circle all of them?
Okay? You have to know what your calculation is. You have to make sure that you're doing the correct units and you're using the correct numbers. The answer to this question is 102%. There will be lots of wrong answers that involve punching random numbers that are provided to you into the calculator. Okay? This is a full-length question that's really deserving of something like 151. Okay? And it's really just presented here. Remember, I just solved it through for you with a little bit of your help. Okay? Not really expected of you of 130. It might be on the order of, I don't know, like an extra credit question. Okay, or maybe broken down into pieces for a short answer.
It says the chemist recorded a dry mass of 60.0 grams.
Just because they think it's dry doesn't mean it is dry.
But he's a chemist.
Chemists make mistakes. Have you not seen these lectures?
True. Flawless.
Okay. So we have to be careful within those results, and sometimes we'll get things where we're greater than 100%. We're like, no, I was perfect with that. It was perfectly dry. Maybe you still have some leftover magnesium hydroxide. Right? It doesn't have to be the water. So we will encounter cases where we make weird mistakes. This is why in science, what would happen if we got a result that was 102%? We'd go back and we'd do the experiment again. Okay? And we test it multiple times to ensure that that 102% was real. Because it is possible that we made an unknown mistake. If we can find out where that mistake was, now we could publish those results. But science is not done by doing a single test and then publishing. That doesn't happen. Okay? Usually what happens is running a single test, being like, oh crap, that makes no sense. And so you do it again and again and again. And then you're like at the end, well, that wasn't supposed to happen at all, but it's consistently true. What did that mean? Your initial hypothesis for the experiment was wrong. So what did the scientists publish? They changed their hypothesis, and now they publish their new result. Look at my results, perfectly match my hypothesis. I must be a genius. No, you jerk off. You just changed your hypothesis and then told everybody that.
No, you burnt nut.
Oh my God.
Should we let you guys have a moment? Okay, so why is this question so much more difficult than any of the others? Well, let's look at the things that have to be answered. You need to know that the formula for magnesium hydroxide and hydrochloric acid. You had to know what type of reaction occurred. You had to determine what products were yielded. You had to balance the equation. Okay? Maximum yield of magnesium hydroxide was the limiting reagent. Maximum yield of hydrochloric acid was the limiting reagent. Which one was the real limiting reagent? What are actual and theoretical yields? Actually calculating the percent yield. Okay. Okay. Which is one of the reasons why you go through the class. What you're trying to do is say, what are all the things that I had to think about and process through to solve a question? And it is the approach to solving the question that you should be getting out of the class. Right? It is going to be exceptionally rare that anybody is going to pass through this class in my career wanting to do this for the rest of their lives. Right? That's just not going to happen. And that doesn't mean the community college. That means kind of nationally. Okay? That is exceptionally rare. Okay? So what you need to get out of it is not the content, but how did you process and organize those steps? When you tried to go through and solve, did you immediately say, what is the actual and theoretical yield? Those are the answers I calculate. You said what I needed, okay, percent yield. Oh, but I need the actual and theoretical yields to determine the percent yield. To determine which one was actual and theoretical, what did we need? We needed the chemical equation. To get the chemical equation, what did I need? Oh, I had to go back through and figure out all those different pieces. Okay? So all of those things stacked into it, and it's the logic and organization behind how you solved the question. That's what you're supposed to be getting out of the class. Okay? That's what takes you forward in your future careers. Okay? That said, almost everybody has to do conversions. That's just a feature of life. Okay? So, conversion factors, where to find them. We've already talked about this. This is one format for how you could go through and find those conversion factors. There was another format. Right? Ultimately, the biggest thing to realize is get into moles. Because moles allows you to convert substances. That's the biggest deal out of chemistry, is moles allows us to use a chemical equation. So when in doubt, convert to moles. Just do it. Okay? Make sure you use a proper conversion factor. Okay? So you have to know what those conversion factors are, which could then come to, whoops, not on that slide. I thought it was the exam sheet, but it wasn't. Okay? Which then comes to kind of the exam. You have a note card. Put on that note card where to find those conversion factors. Putting the conversion factor between grams and moles for magnesium chloride is great. That's a conversion factor that you will probably never use on the exam. Where do you find the conversion factor between grams and moles? The periodic table. Okay. So putting some kind of note on your note card that that's where it's found, that is now useful information. Does that make sense?
I just want to point out something.
Go for it.
What's his name was bragging about never being absent? He's absent today.
Who?
Just saying. I mean, homeboy right here.
So So James, when you get home and listen to this, you just got called out. So to our last topic, after that little segue, we have empirical formulas. So this comes back to a chemical formula. Okay? What is our formula for sodium chloride? What is our formula for magnesium chloride? Cl2. Why is MgCl2, or magnesium chloride Cl2, and sodium chloride is only Cl1?
Because it takes 2.
Why does it take 2? To balance the charge. Magnesium's a +2, sodium's a +1. So if I know those charges, I can predict the amounts in those. So those numerical values, okay, the implied 1 next to sodium, the implied 1 next to chloride, and the implied 1 next to magnesium, and then the given 2 next to chloride are a count. How many of those things are necessary to make that molecule? That's why they're there. Okay? Do we have another unit for counts than just the number of atoms? We can convert the number of atoms to something else using
Avogadro's number.
Avogadro's number. What would we be converting those atoms to? Moles of atoms. Guess what the units are on the 1s and the 2s? They can also be used as moles. Okay? Which gets us to the next observation for our empirical formula. The empirical formula is the fully reduced whole number ratio for the elements in a compound. Well, the salts that we've worked with are always the empirical formula because that's how they reduce to balance out those charges. But what happens if you don't have an ionic compound? What if you have a molecular compound like benzene? Whoops. Sorry, let's not make abbreviations. If I drew out the structure of benzene, you're not responsible for knowing this, so don't freak out. The structure of benzene, that is. Here's my structure of benzene.
Is that with an acting medication and stuff like that?
No, it's usually benzene sulfonic acid. Or something like that. Okay, so you might see benzene as a compound floating around. Typically, you won't see benzene, at least not anymore, because benzene is toxic. Okay, it's a carcinogen, so we typically try and limit your exposure to benzene because that's nasty. Causes cancer.
That's bigger.
Okay, so if I looked at the molecular compound benzene, there's its structure. Okay, so what would its formula be?
1, 2, 3, 4, 5, 6, 6.
C6H6. H6. That would be a decent molecular formula. Okay, is that the empirical formula? No, the empirical formula says I want the fully reduced whole number ratio. So what would the empirical formula for C6H6 be? CH, the fully reduced ratio. So how could I reduce those 6's? Well, divide both of them by 6 and they both become 1. So there's the fully reduced ratio. Okay. Why would I look at the empirical formula? So it makes a lot of sense for an empirical formula for ionic compounds because what we're trying to do is those are massive structures. Right? We have tons of metals and nonmetals interacting with each other in a much larger network. So I don't want to keep changing the formula for a different amount of the compound present. So I go all the way to the reduced ratio. If I go through and look at a molecular compound, that is a single molecule of benzene. If I now add more benzene to it, it does not form chemical bonds to other benzene structures. They interact weakly with each other. Okay. So it is its own independent unit. Why does that become important? Well, is C1H1 a formula that could apply to a whole bunch of different carbon-hydrogen compounds? Yeah. That formula is not particularly useful for me. So if I look at benzene, it's more important for me to look at a molecular formula. But to get the molecular formula, I have to know something about the empirical formula. Right? So that's what we're addressing here, is how do we get the empirical formula first and foremost. After we get the empirical formula, how could we get the molecular formula? Right? The biggest meaning that comes out of this is, what are the units on those numbers? What are the units for the 6s? What are the units for the 1s? Because the substance is carbon, right? The substance here is hydrogen. What is the unit tied to that? 1 is a number. Mole is ultimately the unit we want to work with. Atoms would work also, but atoms are so tiny they aren't easy to work with, so we really want to deal with moles. Right? That observation in and of itself is the biggest part of the empirical formula. Recognizing that your formulas give you moles as well as atoms. Okay? So what we've got here is your steps. This is literally what you need to do. I don't like typically going through and just giving out steps, but the empirical molecular formula as a technique is becoming less and less relevant, so this is ultimately just another way to force you to memorize how to do a calculation. Okay, so I'm not a huge fan of that, so all you really need to do is know how to do it. What we just addressed gets you all of that information. Okay? So let's take a look at an example. An unknown compound of radium oxide is found to contain 0.726 moles of radium and 2.3 grams of oxygen atoms. 12.3 grams, thank you, of oxygen atoms. What is the empirical formula? Well, our empirical formula is going to take the elements that were there, radium and oxygen, okay, and it's going to combine them in some either atom or mole amount, X and Y, because I don't know what those are. That's the whole point, is figuring out what those numbers are. Okay? The units on X and Y need to be moles. Right? For radium, what am I told? Okay. I'm told that X is 0.726 moles for radium. Awesome. I'm directly given a number that I could put into my formula. How about for oxygen? Okay. The oxygen, I'm told, kind of running out of space here, but we'll throw it down here. I'm going to regret that in a second. 12.3 grams of oxygen atoms, so just O. Is grams of O the unit that belongs for Y? No. What do I want for Y? Moles, because that's what's in a chemical formula. So what do I have to do to that gram value? I need to turn it into moles. Okay? So there's my first calculation. I'm going to take 12.3 grams of oxygen, and I want to convert it into moles of oxygen. How do I do that conversion? Well, I need to get rid of grams and get moles. Where do I find that conversion factor? Periodic table, and that number would be 16 what? Moles? 16 grams of oxygen is 1 mole of oxygen. I could enter that into the calculator, and I get the magic number of 0.769 moles of oxygen. So cool. The answer that I should go through and write then for this whole kit and caboodle would be radium 0.72, sorry, there's a 2 there. 726, pen, come on, 726, oxygen 0.769. And that is now my answer. Have we ever done that before?
No.
No. What is the empirical formula?
Density
The reduced whole numbers. Is 0.726 a whole number? No. Oh well.
Oh, so that's one.
No, you can turn around, London. Here's your oh well. Turn around.
Man,
Bye.
go home.
Why?
Watch a video today.
Yeah, you might want to watch the video for the part that you missed, because it's useful information. We need the whole number ratio. How can I get a whole number ratio?
Round.
What is a ratio? Comparing two things. So I want to compare those two numbers. I'm going to divide them both by 0.726. I'm going to divide them both by the same number, the smallest number. And I'll divide this one by 0.726. What do I get as an answer? Well, radium will become 1.726 divided by 0.726 is 1. It's okay. So, and this may sound silly, but it is easy to make those mistakes. This is why we have a calculator. Even if you've got a simple calculation, just enter it into the calculator. Okay? Because that may at least give you enough pause to be like, oh, that was really dumb. That's fine. You can fix your mistake. Okay? What is the oxygen? 1.059, okay, which is roughly 1. Our answer becomes
Bless you.
rao, like the pasta sauce.
Row.
Okay? It's a pretty good pasta sauce. Dang it. But I am not selling it.
Does it have radium and oxygen in it?
No, it doesn't have radium and oxygen. I would hope not. That is now my empirical formula, and I have my answer. Okay? This is for an ionic compound, and ionic compounds we don't really have to do empirical calculations for because we could balance them with the charge. Okay? Radium has what charge? 88, left-hand side of the column, bottom.
Ooh, that's going to be a +2.
That's a +2. What is the oxygen?
-2.
What would our formula be? 1 to 1. Okay? So this sets us up with the basics behind it, but it's a bit of a silly calculation because we could have done that without that. Okay? So let's switch it up. An unknown sample was found to be composed of 24.0 grams of carbon and 2 grams of hydrogen. Okay? What is the compound's empirical formula? Okay, so again, what we're trying to solve for, CXHY. I need to know what X is, I need to know what Y is. Our units for X are moles of carbon. The units for Y are moles of hydrogen. Are those the given pieces of information?
Bless you.
No. So what do you need to do? Calculate that up. If you got questions, raise your hand. So the first thing, let's solve for moles of carbon. What am I given to start with as far as the carbon goes? Given 24.0 grams of carbon. That's not the same thing as moles of carbon. How do I do that conversion? Use the periodic table. 12 grams of carbon is 1 mole, and I would get 2 moles of carbon. If we go through and do it with the hydrogen, I'm given 2 grams of hydrogen. 1 gram of hydrogen is 1 mole of hydrogen. My answer becomes 2 moles of hydrogen. I go through and put this together, and I get my answer as C2H2, and I'd say there's my empirical formula. The empirical formula must be the fully reduced. Is that fully reduced? No. To reduce it, I would have to divide both numbers by 2, and I end up with CH. There's my empirical formula. Okay, kind of makes sense?
Yes.
Okay. You're stringing together independent calculations and putting them together into one ultimate meaning. Okay? Are you good? Can I move on? It looks like people are writing, so I'm not sure I should move on. Are we okay to move? We good? An unknown sample was found to be composed of 24 point. This looks awfully familiar. What is compound? A small amount of the same sample. You mean that sample? Yes, that sample. Okay. Was tested using a mass spectrometer. Don't stress about what that means. Ultimately, what it does is it just tells me that the molar mass of the original compound was 78 grams per mole. What is the compound's molecular formula? See what you can come up with. If you do that. Do we know what the empirical formula was? That was C1H1. Okay. And we are told that our compound was CXH something, and that if I add up the molar mass of that, I get 78 grams per mole, right? That was stupid. Okay. So what if it was C2H2? Well, then what would the molar mass be? Well, carbon is 12. If I have 2 carbons, it would be 24. Plus the 2 hydrogens, I'd be 26 grams per mole. Is that my answer? No. So what could I do now? I could do C3H3. Okay? And I could slowly work my way up to eventually get there. Some of you are starting to notice that that's not going to work. Okay? Or that would take a really long time. What is the shortcut? Take 78 and divide it by 13. You get 6. What does that mean? 6 of the C1H1s fit within CXH6, which means X is 6. And my empirical formula, or my molecular formula, is C6H6. Okay. If I divide the molecular mass by the empirical mass, I get the whole number ratio by which I have to scale everything up. Right? You can just guess and plug and chug. That takes a lot more time than I would recommend, okay? Particularly if it was a formula like C6H6. Okay? Divide, that sets you up with the ratio. You can just fix it. Make sense? Okay. Let's see, what did it say to solve for the molecular? Determine the molar mass, the empirical formula. That was one of our first steps. Divide the molecular molar mass by the empirical molar mass. Yep, we did that too. Multiply the empirical whole numbers, 1, by the number from step 2. Oh, we did that too. These steps perfectly outline what you need to go through and do for that solve. Does that make sense? Okay. This next slide is a little bit different, and I don't want to spend potentially 5 minutes, but let's take a couple minutes here. Okay. And it doesn't necessarily have to be a reflection, but what I want you to do is think about these questions. Okay. What new content are you responsible for? Okay. What stuff do you have to know for this test? Okay. Where are you having problems? Where are you not having problems? Okay. Everything doesn't work for either of those. Okay. I want specific topics. Because once we have topics, then what we can do, because the next slide is almost, okay. 3 slides later would be the end of the slideshow, right, where we can then go through and look at the practice exam and look at example questions about those content areas. So if you can identify those weaknesses, we can then directly tie those, or I can find them faster than just scrolling through. Make sense? All right, so spend a couple minutes, see what you can come up with.